we will release that solution. But I'm going to go over these problems quickly today, and if we have time. And mostly, for me, most important thing today we're going to cover is I want to highlight all the important key points I believe is important for this class, and at least for the lectures we covered so far, and so we can agree on what kind of problems are fair games and in midterm. So that's what I'm going to do today. Then let's hope the server works. Uh-oh. It's not. Let's try another one. Oh. Always afraid of this. So, what's the default file names for the modern word? Is that DOCX or something like that?
Yeah,
DOCX, right?
that word is DOC, but
Yeah, but I'm pretty sure it's a new one. Let me try one more time. Otherwise, I need to go to my Dropbox. Oh, come on.
You have the class number in front of.
Yeah.
Should be in front of it.
Oh, class number is different?
You just don't have.
Oh,
it.
yeah. That's a good point. I made a mistake. I should have the class number in front of it. That way, yeah. That's a good point. Otherwise, so that's very important, right? And otherwise, the path is not correct. Thank you. Okay, so I created this file, very simple file, and obviously you can either make notes. I will send out later on. And so the idea of this, the idea of this. Control plus. Oh, it's slow. So this software becomes too smart for me and recently. So let's use this. And these are the highlight points I intended to make sure everyone review them. And the midterm problems will be picked out of these topics, okay? Literally, I will look at the list when I make my midterm, and I will make my midterm tonight. I know tomorrow, and some of you will take it beforehand, and just drop me an email, and in the morning, and I intended to hold this alternative exam, makeup exam, whatever you call it, and between the 3 to 4. And if you cannot make it, let me know, and in front of my office, okay? You can just come in, and my office in the 429A and Harris building, so I'm sure everyone knows that. And so that's pretty much it. And you just come by. So let's look at the smart feature. What's that? Must be some button. Oh yeah, must be this guy. Yeah. So yeah, use here. I suppose there's some zoom feature.
do you use the
Feature width. Yeah, that's my favorite scale. I think that should be default anyway. But so here's the main items. Let me go over them and basically explain a little bit what I mean by this, right? Just by looking at it, maybe you have some, it's still not clear. So basically the midterm consists of two parts. The first half is about the Verilog basics. I know we touched a little bit on the HDL, but just yet another language, fundamentally the same, right? Therefore, we focus on Verilog language. So the second half of this midterm is about the architecture for delay performance. We spend a lot of time, a lot of lectures on this. So obviously the second one are kind of more important. They are more practical and probably more useful in the future. And the first one, and so the first topic I covered is about different abstraction levels, right? And so basically the idea is that when you describe a piece of digital circuit using one of the HDL languages, such as Verilog, and you need to choose which abstraction level you are going to describe this circuit with or at, right? And so we start with the highest level. The highest level, almost literally like a software code. Basically, it's kind of like the algorithm level or behavior level. In Verilog, we don't call it algorithm level, we call it behavior level. Basically, you describe the behavior of a piece of digital circuit. You don't worry about the details. The good example of that is that if I ask you to implement the adder, and you have two 8-bit wide binary numbers coming in, and you will output the sum of these two numbers, assuming all the numbers are unsigned, so on and so forth. Just ignore all the little details. Then, if I just ask you to do that without any restriction on it, and it's very easy. All you need to say is assign C equals A plus B, declare ABC as all of them 8-bit wide numbers, right? That's it, okay? Plus a little bit of declarations. Obviously, that's very simple. However, that description doesn't give you any clue how big this adder is, how exactly you do the adder. And if you can recall, in digital design class, we actually spend quite a bit of time to basically discuss different kinds of adders, right? Rip carry and carry look ahead. There are also some exotic ones out there. And people actually spend almost 50 years to study which adder is the best in terms of a certain performance matrix. There's actually a book, a very thick book, 300-page book, written on this topic, how to design different adders. And the reason of that is very simple. Adder is kind of like the beginning of any kind of meaningful digital circuit. The reason is once you can do the adder, you can do the multiplication. You can also do the division. You can do the exponential. You can do all kinds of crazy stuff, starting with the good adder, right? Therefore, adder is very important. If you get a good adder, all the other things can also be good in terms of performance. So that's what a typical behavior level means. And this is also very important. If you think another important component we typically deal with, which is flip-flop, right? We all love flip-flop because it's kind of like the building block of any kind of sequential circuits, right? You must have some kind of registers somewhere, and flip-flops are very important ones. Now, if you think about it, if we ask you to use a Verilog code to describe a flip-flop, and you could easily use always at, so on and so forth, clock edge, so on and so forth. Then if D flip-flop is very easy, just move a number into output. That's it, right? Every time when clock edge is sensed, you do the registration, data registration. That's it, as simple as that. Then that implementation also doesn't tell you anything how this flip-flop is made, right? And we know we also spend a lot of time in digital design. We learned how to start with logical gates. Now, the first thing we build is what? A latch, remember? And we also spend a lot of time to discuss where does this latch idea come from, right? We use this, so this a smart person decided to connect one gate output back to the input, and you start to see this oscillation of signals. I mean, if you have no idea what I'm talking about, go back to review the logical design notes. I feel like this material is fascinating. But anyway, so that's the idea. We use logic gates. We first implement the latch. Then we decide to bring in the idea. We use like two-level latches and build a single piece of flip-flop, right? And we use this very interesting structure. And it's kind of like a double door structure, if you remember, right? And again, this material also very interesting. Now we took these ideas as granted, but in reality, they are fascinating ideas. These ideas are really, really great ideas, right? So again, if you use a behavior level to describe this circuit, it's very simple. If you use the structural description level to describe this circuit, then it's much more involved. You need to literally instantiate different kinds of gates. Now you need to use wires and connect them, right? Of course, in Verilog, we use name action to basically connect them. Make sense? And here, there's another point I forgot to mention, which is how to connect the wires, right? And if you remember, and we use name matching, and that's one way to do it. And another important point of the name matching in the Verilog is sometimes when we instantiate a module, that module has lots of inputs and outputs. And if you look at the real implementation of digital hardware, for example, if you open up a module implementation from one of the big companies like IBM or AMD, you will see this crazy module has like hundreds inputs, outputs. No one will literally memorize them and check one by one. So the only way to do the connections by name matching is to use a special mechanism, what's called. It's basically, instead of using the order of the input output ports, you use the name instance, right? So literally, so if let me just, I want to draw this. Let's hope the word is better interface than Adobe's. So essentially what I'm trying to say is that suppose it is better. And so if you have a module, you define it, and you define it as ABC, as input outputs, right? And later on in a bigger module, you want to instantiate this ABC module. Let's say you make an instance here. And you want to connect these three wires, three input output ports to different location. Let's call it XYZ, right? And one way to do it is you just instantiate the module and put the real signal names in its place, in order. If you keep the order exactly the same, then all the connections will be correct. Of course, we said if this module has zillions of inputs and outputs, it's really difficult, right? Most of the time in the real module implementation, in the real circuit, and you will find out in the industry, typically you design module with zillions of inputs and outputs, but in the reality, whenever you use it, you only use a very small portion of it. So a lot of inputs and outputs are actually unused. You see what I'm saying? So that way, it's really difficult to, really tedious to just match in the order. Instead, you use names. You basically do something like this. You do like a dot A. Basically saying, hey, I'm going to connect this signal A port in the original module. And I connect it with a real signal. Maybe I call it X. Make sense? And the dot B, and I connect it with Y, so on and so forth. So that's a very interesting way to connect signals, and you definitely need to know it because that's what you're going to use. Of course, we don't want you to just memorize the different abstraction levels. We want you to understand it, right? You have behavior level, logical level, gate level, RTL level, all these different names. You just need to understand what it means typically. We're not going to ask you to recite these definitions. And I typically don't ask the question, so what's RTL? Something like that. I don't do that, okay? If I wanted to test whether you understand what RTL means, I just give you a piece of circuit, ask you something question about it, right? So it just makes more sense. We're not doing the literature, English literature, right? Learning or something. So this is the first item. The second item is the difference between the combinational circuit and the sequential circuit. And I discussed that quite a bit in the class. And the key difference between these two circuits, two types of circuits, is one circuit doesn't have memory. Another circuit has a memory. When I say memory, basically, as another way to say it is one circuit, the combinational circuit, its output only depends on the current inputs, nothing else. Make sense? If you apply the same set of the input values to the same combinational circuit, you should expect the output the same. It will be the same, right? That's what a combinational circuit means. It doesn't have memory, doesn't depend on anything else, only current inputs. The sequential circuit actually, obviously, conceptually, is quite different. Sequential circuit typically have something called a state information inside the circuit, right? And when you decide what should be the output of a piece of a sequential circuit, and that output not only depends on the current input values, also depends on the history of this circuit, the past, the previous applications of input signals, right? In some extremes, you literally would have a piece of a sequential circuit, doesn't have inputs at all. only has output. What kind of circuit is that? Do we know example of a circuit doesn't have inputs? I mean, when I say inputs, the typical inputs, right? And only has output. Output keep changing every time a clock signal, a clock edge comes in. Now the output changes. Yeah.
Random number generator?
Say it again.
Random number generator?
Yeah, random number generator, that's one example, good example. Another one, typical one is counter. Any kind of counter, typically like that, right? The counter, once you turn on the power, the outputs just cycle through some binary sequences, right? And there's no additional input needed. So in other words, the output really depends on the past history, right? Random number generator is a kind of interesting example. It doesn't look like it depends on the past history, right? After all, the purpose of a random number generator is try to generate what? Random numbers, right? If they're random by definition, it shouldn't depend on anything. But in reality, that's not true. Why? Because anytime you use a finite size logical circuit to generate the random numbers, you are not really generating real random numbers. You're generating something called pseudo random numbers. And they're in inherent sequence. You just don't see it. But this long sequence, long period, you need to repeat itself. But that's kind of like the outer scope of this class. We don't need to worry too much about it. The only true random numbers you can rely on is what? You take advantage of some kind of real physical behavior. Because our physical world literally is always random. Anything you can sense is random. Although sometimes it's random with a very tiny range. The mean value is pretty large, so therefore you don't worry. For when you listen to your music, you do realize there's lots of background noise out there. It just if your video player or audio player is good and reasonable, and the noise level is below what you can notice. That's it. When you watch a movie, there's a lot of noise, pixel noises. You just don't see it. Our sensors are not so sensitive after all, right? And so on and so forth. So the real random number generator would be, you just sample any kind of random behavior, like some noise. You just use a sampler to sample it, take its binary values, and that's true random numbers. Talking about the random numbers, we did learn one piece of digital technology to generate reliable, cheaply random numbers. What's the called? Anyone?
Linear feedback register.
Yeah, LFSR, right? Linear feedback, right? LFSR, and sequential register. So that's kind of like a standard circuit item we typically use to generate any kind of random numbers, right? So that's kind of like between these two. Obviously, when we talk about the variable programming, the difference is pretty simple. Anything, if you see a continuous assigned statement, typically that means that piece of logic is implemented with combinational logic. Typically, when you see always add something, that's supposed to be some kind of sequential logic. Typically, when you see in your code, there's some memory elements, whether it's registers or some kind of memory block or whatever, that typically means that's sequential logic. And that's not to say we cannot use always block to implement a piece of combinational logic. Indeed, we can use always block, always add something to implement a piece of combinational logic. But if we want to do that, what do we do typically?
Just use the sign.
Always, typically we always use a wild card and a signal, like which is a star, right? Sometimes we even lazy, we just remove the sensitivity list. You basically literally have always empty, then you have this block, begin, end. That way you also get almost like a piece of combinational logic, right? And also remember in the class, I did mention this way of implement combinational logic is subtly different from using the continuous assigned statements. There's a tiny difference in terms of the simulation time, right? And so think about it, right? That's one way to think about it. And in terms of programming, you do notice the difference between the combinational logic and the sequential logic, right? And so that's very important, right? And before we move on from this topic, I also want to emphasize another concept which we will use later on when we talk about the grid path delay, so on and so forth, right? So one way to think about the digital circuit is, that's also the key idea behind the RTL level description, which is any kind of a digital circuit, you always can look at a piece of digital circuit in terms of a bunch of flip-flops, lots of them, right? And sometimes these flip-flops are in groups, sometimes they are individual. But in any ways, there's lots of flip-flops, and maybe different kinds of flip-flops. These flip-flops will be interconnected through some kind of very complicated network. And we use this little cloud symbol to represent any random combination logic. So between these two guys, maybe you have some piece of random logic. These random logics are obviously can be different, right? So you can see, right? This kind of thing. Obviously, my plot here, or my diagram here is too simple, right? The real digital circuit is much more complicated. And this is almost like the universal way to look at any kind of piece of digital logic. And I don't care what kind of digital logic you're looking at. You could look at AMD, the latest microprocessor. It can be drawn in this kind of diagrams, although that diagram would be huge. But nevertheless, conceptually, it can be done this way. Now, the benefit of doing this way is this is kind of graph. First of all, it's graph. This graph has lots of nodes, right? And this graph also has a lot of edges. And this edge has a little piece of logic attached to it. So that's kind of like a very universal way to look at any digital circuit. Now, once you look at the digital circuit this way, suddenly you can use all kinds of crazy algorithms to analyze this circuit. That's the beauty of doing it this way, right? Otherwise, any kind of digital circuit, you either look at the equations or you look at these logic diagrams, and there's no easy way to manipulate this digital circuit. Once you put it into a graph form, a graphic form, suddenly everything becomes altogether. And all kinds of crazy computer science related algorithms can be utilized to analyze this. For example, if I give you a crazy network of digital circuits like this, then I ask the questions, and what's the longest path between the input and output? I can literally use a graph traversing algorithm to analyze this graph, immediately give you longest path. If I ask the shortest path, I can give it to you. If I ask from this input to this output, how many signals got affected by this input? How many signal paths are related to the output? This is basically, I'm saying, hey, I have this crazy network or graph of a logic circuit. Here I have input like this. I have output like this. And I'm asking how many different signal paths can allow this input to this output. So literally you traverse this graph, you find out all the possible different signal paths from this to this. This is actually quite important for a lot of things, for analyzing the circuit, for decide how good this circuit is, to estimate the performance, and also sometimes even give you the idea how secure this circuit is. So there's lots of crazy things can happen to this format. And that's the whole idea. So which is US is really leading to. I mean, a lot of people talk about manufacturing or this kind of thing, but really there's one area US is really leader in the whole world is EDA. EDA stands for what? Anyone know? Electronic Design Automation. Exactly. So that includes literally 3 companies are really doing it. One is that Cadence. Everyone heard of it? Another one is what? Synopsys. Another one, I forgot the name. It's not typically you have 2 big guys dominating. The third guy just barely competing, right? That's typically happens in every industry in high tech. So in this area, only US does it. No other countries even come close. I don't know why, but that's the reality. And so all the software you're talking about really is EDA softwares really deal with this kind of data format, and they use all kinds of crazy algorithms. That's obviously a lot of IPs inside this. So if you guys are interested in working in this area, definitely you should really focus on this. And the exciting thing, the most exciting thing recently about the EDA industry is all about AI. And no surprising, right? And everyone's talking about it. And although I look at the most of the companies' websites, they didn't mention that. But when you read it through what they're talking about, it seems like a majority of them they don't know it. They just basically say it, try to pretend they are in the game, right? And there are some really big companies that are secretly doing it and get a really good results, but obviously they don't tell everyone. They just secretly do it. And one example is Google, right? Google has this tremendously powerful AI engine to do the chip design. One particular problem they're focusing on is when they design the chip layouts, how do you make the layouts very efficient, make it very compact and also high performance? That turns out to be extremely difficult problem to solve. And they showed they can use AI, some kind of crazy AI algorithm can make the design really, really beautiful and also very, very efficient. And it's much better than the human solution, the manual solution. We used to rely on human experience to do this kind of thing. And obviously it takes a lot of time. And in the end, no one knows whether that result is the best you can do. But use AI, it's much better, much more efficient. So it's a lot of exciting things happening in this domain.
My girlfriend's uncle is a radiologist, and
Uh-huh.
they've been trying to use AI for brain scans.
Oh yeah,
They're
they
finding-
use that all the time. Nowadays they use a lot.
I think it started with like Watson or something, right? For my
Yeah, they even use the AI read the CT
yeah.
to detect the early stage lung cancer, this kind of stuff. I mean, it's a lot of crazy things.
It's a lot more accurate.
yeah, so and also in the legal industry, it's a no-brainer. The paralegals, the jobs of paralegals will disappear very soon, right? And but that's unfortunate for them. But I hope like these people can be shifted to other more valuable industry. That's what happens, right?
Yeah.
And a lot of old jobs just disappear, and it's sad. But you cannot hold on to it. You know, I read some interesting story the other day. There are literally a job, a very prominent job in like 16th century England or something. They literally every morning there are some people literally go to each door, just throw a little stone to the window. You know what they're doing?
The alarm
They wake people up because at the time there's no alarm clock. They literally hire people to every door, just knock the door, literally. Use the little, obviously they are very skilled. And they can knock the window without breaking the window, I guess. But that's the problem. So I using this example, it's a very good example of saying, hey, certain jobs you just don't want to keep it, right? You move on. You cannot just cry for it and stay in the same place. Anyway, so that reminds me another, I know I'm talking too much. Reminds me of one period of time. You remember there's a scare about like 2,000 computer like a crash. Yeah, I forgot the term for it. Yeah. Basically, everyone is panicked. Like as soon as the clock passed through the 2,000 something, and all the computers will crash or something. So basically, it turns out to be a total bogus, right?
Nonsense.
Yeah, it's a total nonsense. And at the beginning of the email, a lot of people are really mad because the postman job or mailman's job will be gone. And look at today, and their business is bigger than ever, right? There's all kinds of, not only their jobs are there, and also there's a lot of private companies doing the delivery business. They're competing like crazy. But bottom line is, we don't need to worry about the advances of technology. We need to worry about how we can come up ways to utilize it. So don't worry about the robots. Don't worry about automation. Don't worry about AI. So nowadays, everyone talking about AI is so scary. You kill us, something like that. It's not right. And I don't understand people, the way people think. But anyway, so move on to the blocking, non-blocking. I believe everyone already know. Blocking, non-blocking, basically talking about two kinds of statements, right? And if you use the equal sign to assign signals, that typically is blocking. Meaning you have several statements one by one. If you use equal sign to assign values, these statements will be executed one by one in order, literally as if one is blocking the other, right? And so on the other hand, in Verilog language, if you use this little arrow thing and less equal, and that means assign statement. Still assign statement. It's not less equal, right? It's assign value from the right hand side to the left hand side. If you use that, if you have several statements like that, and it literally means these statements will be executed at the same time. They don't block each other. That's why we call it non-blocking, right? And of course, we use a very example. Typical example we typically use is to demonstrate that the difference between these two is two kind of example. One example is a shifter register. And you can go back to the lecture notes, you can see it easily. And without this non-blocking, the shifter register would be harder to do. Another one good example to demonstrate the difference between these two is using the swapping, right? Swapping and swapping statements. And if you use sequential, you have to create a temporary variable to hold the intermediate result, right? If you use non-blocking, you can use two statements to accomplish this swapping, two variables, right? So this is the third one. The move on, the next one is synchronous and non-synchronous. And this one, obviously, we talked about, mostly is because most of the circuits, 99% of digital circuits we're dealing with today are literally driven by some kind of clock signal. And the synchronous design means this design is controlled, is driven by a well-defined clock signal. And in the context, synchronous versus non-synchronous, what I really meant is some variables. When you use some variables to control the behavior of a circuit, do you want to control the synchronous way or do you want to control the asynchronous way? Asynchronous way basically means you literally want to change the circuit behavior at any given time you want, right? Synchronous way basically means even if you request that change, but you have to wait until the next clock edge to arrive. So the change only can happen when the clock edge arrives. Otherwise, nothing will change, right? Of course, when your clock signal is really high frequency, the difference between these two are quite minor, right? And in terms of variable programming, for synchronous, you need to put this particular variable you use to control the circuit into the sensitivity list, right? Always add something, and you put it in there, in the list. That way, that thing only can give you sense. Oh, I think I reversed it, right? You actually, if you put it in the sensitivity list, that's actually asynchronous. Everyone thinking so? No one objects to what I just said? What I'm saying is like asynchronous versus synchronous, right? If I'm using a variable called x to control the behavior of my circuit, and where should I put it? If I put this x variable inside of my sensitivity list, am I implementing an asynchronous or synchronous circuit? Asynchronous, right? Because that literally means anytime this variable changes the value, I need to immediately execute something inside my block, right? And on the other hand, if you only allow synchronous change, you need to remove that x variable from your sensitivity list. Then obviously you still need to test that variable inside your block. Make sense? That testing only can happen when the clock edge arrives. So it's very easy to mix up, but you got the idea, right? That's what we mean. And typically we're talking about reset signals, right? Set signals, reset signals, maybe some other certain signals, so on and so forth. Okay, so this is D. And what about the E? Active low, active high. This obviously is just convention of the digital circuit domain. And active low basically means 0 means positive, or 0 means assertive, 0 means turn on, basically. I think 0 means on, probably is more appropriate to say this. Active low basically means 0 is 1, 0 is true, 1 is false. On the other hand, active high means 1 is true and 0 is false. So there's just different ways to think about it, and you need to pay attention to that, because if you draw the digital circuit, if you look at your digital circuit implementation, this difference actually is important. Another important active high, active low is that regarding to the rising edge and the falling edge of clock signal, right? You could use a rising edge to drive your signal, to drive your circuit, or you could use the falling edge, right? Falling edge is from 1 to 0, rising edge is from 0 to 1. Sometimes people talk about the positive edge, negative edge. Positive edge means rising edge, and the other way is falling edge, obviously. So there's different ways to call it, but fundamentally, either you use the positive edge or you use negative edge. And in terms of a logic diagram, you see no bubble at the clock, the little triangle thing, and that's typically the clock signal part, right? and either you have a bubble there, or you don't have a little circle there. If you don't have a little circle there, that means positive edge sensitive. Basically, you act on the rising edge. Otherwise, if you have a little circle there, that means a negative edge will activate this particular circuit. That's all, right? Very simple. This convention, right? You don't have to do this way, but since most people are doing this way, you may as well just follow it. Otherwise, people will misunderstand you, right? You don't want that. So finally, not finally, next one will be 3 kinds of assigned statements. I mentioned in the class, there's 3 kinds of assigned statements. The one is the most frequent one with continuous assigned statements. Typically, it's assigned with the keyword assign, right? And x equals y. We know that. And then the second one is blocking is x equals y. And the third one is x less equal y. And these basically 3 kinds of assigned statements. And the first one is continuous. The second one is blocking. Third one is non-blocking. People say, hey, how do I know when to use each of them? It's very simple. I use very simple rules for them. There may be exceptions. Right? Modern compiler typically allow you to do some little bit of crazy thing, but it's not safe, right? You don't want to, based on your implementation, based on the correctness of your circuit, on some compiler specific feature. You don't want to do that typically, if you don't have to. Typically, the way I use it is very simple. The first one, so the interface standard improvement, this little dot need to be make it more visible. But anyway, so the continuous assign statements always is used outside any always block. Make sense? So if you have a bigger piece of Verilog code, if you want to assign something outside of any always block, you always use this continuous assign statement. That's the only place you use that. And anything inside the always block, you either use non-blocking or use blocking. The next 2, you pick one. Depends on what your need is, right? If you use non-blocking, you use the x less equal. And if you use blocking, you use x equal y. Sometimes you do want this kind of sequential names. You wanted to force some order between these assigned statements. In another way, you use x equal y. A good rule of thumb is when you design digital circuit, you need to really be careful about this kind of like a blocking behavior, because typically you don't need that. So most of the time, your circuit shouldn't need this kind of blocking behavior. If you really need that, you can do something with your circuit design. So typically you don't need that. People tend to use that more often than necessary. And most time you should always stick with this non-blocking, because that's what the digital circuit really do, right? And so you want to use that. Any questions? Let me pause here. And yeah.
What's the third one again? Where you use
third one, this one?
Height, whatever that's supposed to be. Yeah.
You mean? Oops. I need. Okay.
Yeah,
You mean this one?
Yeah,
This
one
is a
block.
non-blocking one. Less equal. Yeah. It's a kind of less. That's just the special symbol Verilog used to define these assigned statements. Right? Make sense? It's not really less equal. I just call it less equal, but it literally just assign statements.
So what would you use?
A left arrow is also a good one. Yeah, that's good suggestion.
That's called.
Yeah, left arrow. But left arrow, almost like the reason I hate that is because it always implies one symbol. But it literally in Verilog program is 2 symbols, right? They just connect them. Invented a new. I treated it as 2 symbols. Yeah. But anyway, yeah, you know what I meant, right? So, okay. Any questions about this? So far, everything is very straightforward, right? Nothing.
So when would you use a sign versus the less equal sign?
Oh, so anytime, I mean, if you look at any kind of Verilog program, you typically have always something, right? A block, always block, always block. Anything outside is always block.
Mm-hmm.
You use the first one.
Oh, anything within
Yeah, anything within a block, you either use this or use this. So the second and third are reserved for any in-block assigned statements. If you just keep this simple rule, you never can be confused, right? And as I said, like a modern compiler probably allow you to do some crazy thing. You could literally put the assigned statement, a continuous assigned statement, inside some block under certain special condition. But I think that's like a useless practice to me, because the one lesson I learned after, I don't claim I'm a good programmer. One lesson I learned after so many years do the occasional programming, one lesson I learned is try to write as much as you can. Don't take shortcuts. Don't play smart with the programming language, because the time you saved by playing smart with it is not worthwhile. Later on, give you tons of headaches and cost you tenfold more time waste. And then you just play smart. So just when you write a program, try to be as clear as you can, and don't take any shortcuts. The same thing happens to this is especially true for parallel programming. Because parallel programming already, the productivity is already low, right? Because it's parallel programming. And debugging is so hard for parallel programming. And the last thing you want is to do something like shortcut thing, right? Just save a couple of keystrokes. Later on, you spend 10 hours to debug your program, couldn't figure out why. So you see my point, right?
That's why I don't do recursion.
Yeah, try not to do that, unless you have really good reason to do that. And people tend to do stuff without asking why they do that. People just blindly do it. And this reminds me of a little story. And there's a lady talking about cooking. And he tried to demonstrate it on a TV show to how to cook a beef or something, roast beef or something. Yeah. What he did is basically he take a whole piece of beef and cut a small piece, put it aside, then started to cook the rest of it. And after she has done this several times, the TV show host basically asked her, "Why do we do this?" The lady answered, "I don't know. I saw my grandma does this all the time. Her grandma also, see his grandma also do it." It turns out the reason is that at the time when her grandma was doing it, is because the oven is a little bit smaller than the meat, so he cut the extra piece, put it aside. So his whatever the cookware is big enough for that piece of meat. Later on, obviously that problem is not there, right? You shouldn't do that anymore. But people just blindly doing it. The reason I bring up this story is like this actually what people a lot of times people do this in the industry. People do certain things just because everyone's doing it. And after a while, no one knows what's the real reason. People just blindly follow it. And this could cause a problem, right, later on. And so a smart thing to do is always ask why. Okay, so next point is how to generate a clock signal. And we showed you many examples, right? The easy way, the cheapest way to do this is use always block and use the time delay statements, right? And here I just want to pay attention to how to, in general, generate any kind of clock signal. So in the midterm, I could say, please generate a clock signal with 9 time units as clock period, 4 time units in each cycle, in clock cycle, and each clock period, and 4 time units for the positive portion, and 5 units for the negative portion, and how to do that. Now, I can easily ask this question, right? This literally gives you the idea, tests your idea how to implement any kind of clock signal, any duty cycle ratio, so on and so forth, right? So, next one is the difference initial block and the regular blocks. And here I want to mention one thing is that the initial block only got executed only once, right, at the beginning of the simulation. Once it's done, never come back. So that's the unique thing about the initial block, right? Other blocks, and you could potentially do many times, but the initial block, and you only do once. And I also in class I improvised a little bit. I said that they're essentially in the Verilog code. They essentially CIA 3 types of blocks. I don't know whether you remember, right? The I stands for initial block. The C stands for, anyone remembers? Continuous, exactly. A continuous is what I'm talking about here, right? This part, right? And once you have this always, that's the A part. Always block is another type of block. So you can easily say, hey, CIA, 3 types of blocks. Any kind of Verilog code can be put in one of these 3 blocks categories. And there's no other ones out there. So this also can be connected to these 3 types of assign statements, right? The first one always goes to the C block. And the second and third one always goes into A block, right? Make sense? So that's what it is. Next one is the module definition versus the module instantiation. And again, here I want to mention, I already kind of like talking about this. This basically name matching is the most important thing about understanding the module definition. Module definition is like in the software, module definition is like a .h file. You basically define the interface. But more than, no, I'll take it back. It's more than a .h file. .h file in C language is kind of like a header file, right? It just defines the interface. It doesn't give you the guts of this piece of program, right? In Verilog is different. Module is kind of like a subroutine or submodule, function definition, right? It gives you not only the interface and also what do you do inside this module, right? Module contains everything. It's like the whole package. But the instantiation basically means whenever you need to use that block, you need to kind of like instantiate, make a copy of that block, put it somewhere. And that's actually quite different from the software. Software, when we need to use a small function, we call it. We don't literally copy the binary file into our binary file, our big binary file. Although I don't want to go to this. In software, sometimes we do copy it. And this obviously has something to do with the dynamic linked library. You know, Microsoft, they have DLL, so on and so forth. They also have a statically linked library, so on and so forth. That literally copy versus not copy the binary file, right? And but here we just focus on the hardware. Hardware means we can define one module, then we can instantiate thousands of copies.